Okay, welcome. We're going to be talking here in this video with a little bit of a overview of what's on your exam. So our exam covers sections 2.2, 2.3, 2.4, and 2.5. The topics, first topic we covered was numerical and graphical limits. So you're going to have some problems where you're asked to compute limits either numerically or graphically. So with numerical limits, very important, you must show a table. So if we go back to our 2.2 notes, we can see several examples of some problems here where we're doing limits numerically. So here we were doing limit as x goes to 3 of x squared minus 5x. So remember, you have to take values a little bit smaller than 3, usually standard tenth, hundred, thousandth below and tenth, hundred, thousandth above. And then you can draw your conclusion. Does it approach something? If so, what does it approach? So this is a limit. Of course, we know analytically we can just evaluate it because it's a polynomial. But when you're asked to do it numerically, I need to see a table for you to have credit. Okay, you must show those values. Again, there's a second example from the notes with the rational function where the values again are squeezing in towards a particular value. Or it could be a case like this third example that we did where the limit does not go to anything. Okay, but you'll have a couple questions where you're asked to deal with limits numerically, and it's very important you must show the table, show the values that you're computing, and then what's your conclusion based on those values. We then talked about graphical limits. So if you go back to the notes, I showed you basically 6 different possible examples. One graphically where it literally goes to the same point as the limit, and so those are the same. Or we could have a case here, limit is looking what it's approaching. Here, same thing, limit is what it's approaching, even though it's different than the function value. Here in this case, it doesn't settle into a single value, there is no limit. Or, as was the case here, it's a vertical asymptote. The two sides are going to positive and negative infinity, so overall there is no limit. Or it could have been a case that it oscillates. Now the numbers that are listed here with graphical limits are a little outdated. They're from the physical textbook is what I'm talking about here when I refer to problems. The numbers are actually a little off now, so I want to show you here. If you go into your textbook, your online textbook, so here under section 2.2, I click on exercises. Then we have our list of problems here with some graphical limits. So here we're doing limits graphically. 17 is a great example to kind of really bring home all the stuff we've talked about with limits graphically and understanding those. So if you look at 17 here, we're given this graph where we have a V-shaped graph, a hole at 0, point jumps up here at, hole at 1, 2, point jumps up to 3, graph continues up to 3, 4, where there's another hole, points defined at 3, 2, there's another hole in the graph here at 3, 1, and then the graph resumes its shape. And we can ask lots of different questions on this problem here based on this graph. So for one instance, we're asked, what's the limit as x approaches 1 from the left, left-hand limit? So we're looking at it as we approach 1 from the left. Taking on values a little bit smaller than 1, we can see that the graph is still approaching 2. The fact that it's 3 at 1 doesn't have any effect on the limit. It's what is the graph approaching. So left-hand limit as we approach 1, in this case is 2. In a similar fashion, the right-hand limit as we approach 1 is 2, so the overall limit as we approach 1 is also 2. Now, problem H here asks about the limit as x approaches 3. So here we are on the x-axis at 3. If we look at the left side, the graph's approaching 4. If we look from the right side, the graph's approaching 1. And f of 3 itself is actually 2. So f of 3 itself doesn't really have any impact on the limit, but what we can see here is that as we approach 3, graphically, there is no limit. There is no limit since the left and the right disagree. Now, if it had just asked limit as x approaches 3 from the left, like it did here in part F, then that thing is approaching 4. If it was asking limit as x approaches 3 from the right, like it does in part G, then that graph is approaching 1. But the overall limit doesn't exist because left and right don't agree. So that's a really good example to kind of refer to, kind of think of the type of question that I will ask on the exam. It's very similar, where I'll give you a graph, maybe it looks something like that, and then I'll just give you a list of some different questions. Maybe not quite so many as what 17 does. That's a really good example. 18 as well. Very good example because that brings in both left and right hand limits graphically. 15 is okay as well. And if you go back into those notes, 6 and 5 and 4 and 3 also deal with some good graphical limits. Now, 3 through 6 doesn't have the left and right hand limits in those questions. That's why I referred back to example 17, because it does a really good job of describing those different ideas. As far as domain, this graph seems like it's continuing, since there's no circle to indicate that it stops here at -1. And also at x equals 5, it seems like it's continuing on. This thing is actually defined everywhere, although it is not continuous here because of the hole, and it's not continuous at 3 because of the jump. Okay, so that's limits graphically. We then moved on to the 2.3, where we talked about limits analytically. We had a lot of basic rules and stuff. The big thing that you're going to be asked to do is to evaluate some limits. Now, some of those limits could be like some of these examples we did here, where we just have things that we can evaluate. If it's something we can just evaluate because it's defined as a polynomial, or as a rational function, or as a radical function, or with our trig functions, and it's something we can just go ahead and evaluate, then we just go ahead and do that. Also, remember we talked about piecewise functions. We also talked about piecewise functions here. A really good example here from the notes is this function here, 2 minus x, x squared plus 2. Left-hand limit is approaching 1. On the graph we can see it down here as well. Right-hand limit, we're approaching 3. And so the overall limit then doesn't exist. It doesn't settle into a single value. And then one of the big things out of 2.3 is we talked about 0 over 0 limits. So if you go down, I would expect to see a problem where you're dealing with a rational function, like these examples here that we did. You can expect that you're going to see something with a fractional function, very much like this example here, where you're going to have a 0 over 0 limit that you're going to need to simplify. You do that by getting rid of the complex fractions. then you can expect that you're going to have something with a radical, where you're going to need to rationalize the numerator or denominator by multiplying to make it a difference of squares. Additionally, we also talked about these two rules. You don't need to know how to prove them or anything, just be aware of these trig limits, because you could have questions involving those as well. We did a few examples here as well. So if you refer back to these examples, evaluating things like sine 3x over x or sine 2x over 5x, or limit of tangent. And then we moved into a discussion of infinite limits and vertical asymptotes in section 2.4. So if you go into section 2.4, basically any limit involving a number divided by 0 is going to be a situation where it's going to be an infinite limit. And remember, the convention that we used here is that if the left is approaching negative infinity, the right's approaching infinity, or vice versa, left and right are approaching different directions, we say that the overall limit doesn't exist. If the left and the right are both approaching positive infinity or negative infinity, then the declaration we say is that the limit is equal to infinity. Now, in all these cases, the overall limit doesn't exist, ever. Limit as x approaches 2 does not approach a number, but we say it's equal to positive infinity to indicate kind of why it doesn't exist. But we still keep that convention. If left and right are different, we say it does not exist. And remember, the way to do that is basically just to test. We know it's going to be infinity or negative infinity. We just have to figure out which one. So when we're asked for a left-hand limit, we just test the signs as we're a little bit smaller than 3 to see what the sign is. Or, as we did in this example here, it was approaching positive infinity, so we need to check. If we're dealing with the full-blown limit of a number divided by 0, then we need to test the signs to see which one it is. If they both go to positive infinity, as happened in that example, then we say the overall limit's positive infinity. If one went to negative infinity and one went to positive infinity, then we just say that that limit doesn't exist. And remember, vertical asymptotes occur where we have an infinite limit, a number divided by 0. The one thing you have to be concerned about here with vertical asymptotes is if it's not a number divided by 0, but rather a 0 over 0 limit, then you're going to have a hole in the graph. And so usually we just look, the easiest way to do these is to look when the denominator is 0, and then does it also make the numerator 0? If it's a 0 you can cancel out, then you just go ahead and cancel it out, and then therefore that's a hole and not a vertical asymptote. So you can refer to that example there. We also did an example with the tangent function. Right, when was the tangent of this thing? When did it have a vertical asymptote? This was a little bit more of a mess, but basically tangent, anytime it's undefined, cosine is 0, you're going to have a vertical asymptote. And then the last topic that we had is this discussion of continuity. You should know the definition of continuity. I almost always ask about that on the test. So going back up, specifically the definition of continuity is you have to have 3 things. Function has to be defined, the limit has to exist, and they have to be equal. Okay, those are the 3 things you must have for it to be continuous. And then what we do is we have some questions asking about when a function is continuous. So these are our conditions, right? And for the most part, unless we're dealing with a piecewise function, if our function's defined, it's continuous. It's continuous. So a rational function, as long as it's defined, it's going to be continuous. So in this example, at -5, it's not continuous. It's also not continuous at 0 because the original function is undefined. Piecewise functions, you do have one extra step you have to go as far as continuity. You can look at your pieces to see when they're defined, but the one question we have to ask is at the crossover point, is the function, is it still continuous here? So this thing's defined everywhere, but f of 1 here was 3. The limit as x approaches 1 is actually equal to 2. So we do have a limit, but it's not continuous because they're not equal. So piecewise functions, you do have to check those. Just because they're defined, you do have to check, does the limit equal to the function value? Okay, or do you even have a limit? Okay, and then the final thing we asked here with these questions was to classify. If we do have a discontinuity, if it's not continuous, we want to classify those as being either removable or non-removable. Okay, so the process basically is if we can compute the limit as x approaches the value. So it's a value where it's division by 0. But if we can compute the limit, then that is a removable discontinuity. So if we have a limit, it's removable. If it turns out it's a vertical asymptote, because we have a number divided by 0, then that's automatically non-removable. Or, if it's like a piecewise function where the left goes one way and the right goes somewhere else, we don't have a limit, so therefore it's non-removable. But if we have a limit at that discontinuity point, either a hole or the function being defined differently, then that's called a removable discontinuity. If we have a vertical asymptote, or if it's a piecewise function where it switches from one to another, then it's a non-removable discontinuity. Okay, so that's our exam. If there's any particular topics you have questions about it further than what I've covered, please send me an email, contact me, and I can hopefully clear things up for you. Otherwise, hopefully this gives you kind of a little feel for what's going to be on the test and the kind of questions. You'll find a very nice connection between problems that I've done in the notes or in the course videos, along with what will be on your exam.